In this 18th lecture, we will discuss model selection. In general, we may write the underlying relationship between the response and the predictors as this. Here, f is an unknown function of all predictors describing the underlying relationship, and epsilon is the error. We may estimate f using f hat, which is our estimate, and may be used as our prediction of y. For linear regression models, f hat is this sum, where p is the number of predictors. If we have a model perfectly describe the underlying relationship f, then we eliminate the reducible error, but we still have the noise as the irreducible error. If the model is not perfect, then we have the reducible error in addition to the irreducible error. The mean squared error is the expectation of the squared difference between the predicted and the observed outcome. If the model is specified, then f hat is fixed. So the mean squared error is the sum of these two terms. The first term reflects the model correctness, and the second term is related to the noise. In practice, we don't know which part of the mean squared error is from the noise. Thus, when the model is not good enough, the model attributes some reducible error as a noise, and we have an underfitted model. Similarly, when we mistakenly attribute part of the noise as the reducible error, we have an overfitted model. For example, we would like to classify two groups based on two predictors, x1 and x2. The purple dashed line is the simple linear classification. However, the straight line is the least flexible and the accuracy is low. This classification may be underfitting. The black linear spline is the most flexible classification. It correctly classifies all data points. It may be overfitting since the spline costs too many degrees of freedom. The red curve seems appropriate. It is more flexible than the straight line and has a higher accuracy than the straight line. From the example, we find when the model is more flexible and uses more degrees of freedom, we are more likely to be overfitting. The overfitted model only gives accurate results on the sample data we use to develop the model, but it may have poor performance in statistical inference. In practice, we usually randomly split all data into two sets, the training set and the test set. We develop the model solely based on the training data and only check the model performance based on the test data. Also, we may use k-fold cross-validation. The data is randomly partitioned into k equal sized sets. Of the k sets, one set is picked in turn as the test data, and the remaining data is used as the training data. Then we average k results to produce the estimation. We may use the model f hat to infer the underlying relationship fx. We may split the sample data into the training data and the test data as we discussed earlier. In a way similar to an estimator, we may have many models for different training data. The expectation of the model is the average of all models. The bias of the model is the expectation of the model minus the function f, and the variance of the model quantifies the spread among the models from different data. The mean squared error of the model is the sum of the squared model bias, the model variance, and the variance of the irreducible error. When we have a simple model with a few degrees of freedom, we may have high bias and a low variance. For example, simple linear regression model is a simple model with only 1 degree of freedom. If there is more than one factor related to the response, then the simple regression model is underfitting. The model will have high bias and at the same time low variance due to the model simplicity. When we use a complex model with many degrees of freedom, we may have low bias and high variance. For example, a multiple linear model with 10 predictors will fit the data better and at the same time more likely to be affected by the change of the data. The model bias variance trade-off is shown in the sketch of the training error and the test error here. In practice, the test data is not involved in the model development and only used in the model evaluation. The test error is the mean squared error computed using the test data. The training error, as the blue line, decreases as the model becomes more flexible and uses more degrees of freedom. But the test error, as the black line, is different. When the model complexity is beyond a certain point, the model becomes overfitting. The training error continues to decrease since the model may include the noise as overfitting. But this does us no good since the test error is quite high as shown in the graph. The test error increases instead since the reducible error increases in the test data due to model overfitting. Thus, the model that gives us the minimum test error is the appropriate model. A model becomes more complex and more likely to be overfitting when we include more predictors in the model. Thus, although we are tempted to include all variables in the model to avoid losing any information, we should not do so in many situations. The number of variables is limited by the sample size, the model structure, the noise control, and the model interpretation, etc. Thus, we need to select the predictors included in the model. There are several basic guidelines that we should follow in the model selection. First, the simplest is best. Don't add predictors for little or no improvement in the model. Unnecessary predictors add noise to the estimation, waste degrees of freedom, and more likely to cause overfitting. This is true especially in predictive modeling. Second, we should keep the lower order terms if we include the higher order terms in the model. For example, in a polynomial model, if we would like to include the second order x squared term, we should also keep the x term, even the linear term is not significant. This also makes the model interpretation easier. Third, add or remove variables one at a time, preferably using the automated variable selection procedures. In practice, there is no perfect selection procedure in many situations. We may combine or compare several procedures to optimize the model. Last, consider the collinearity during the model selection. We studied the interaction effect of the categorical predictors in lecture 14. Here, we learn the interaction of continuous variables. The circled term is a two-way interaction. As we learned, the interaction term may cause the collinearity issue. In many cases, we may weaken the collinearity by standardizing or simply mean centering the variables. In the psychology example in lecture 17, we may regress the overall test score y on x2 and x4 without the interaction. Both x2 and x4 are significant without multicollinearity issue since the VIFs are only 1.27. However, when we add the interaction term, x2 multiply x4 as x6, then all terms are highly correlated and the VIFs are all above 100. The multicollinearity inflates the standard errors. For example, the standard error of x2 is 0.06 without the interaction term. With the interaction, the standard error of x2 is larger than 1. Both x2 and x4 become insignificant. Obviously, the model doesn't give us the correct conclusions. Now, let's use the mean centering on both x2 and x4. x2c is x2 minus the mean of x2, and x4c is x4 minus the mean of x4. After the mean centering, the model has no multicollinearity issue, and all VIFs are close to 1. The interaction term is insignificant, and the model is not much different from the model without the interaction. For example, the standard error of x2 is still 0.06, not much different from the model without the interaction. From this example, we also find that the multicollinearity doesn't affect the coefficient estimation and the coefficient of determination. Both models with the interaction term have a R-square of 0.863. Now, we discuss some automated selection procedure. The best subset selection should be the top choice if possible. It compares all possible models and finds the best model for the specified number of predictors based on the score chi-square statistic. This table shows the best model for each subset in the psychology example. Here we find the best one predictor model is X1, and the best two predictor model is X2 plus X4. The score chi-square statistic is used to find the best model for the specified number of predictors. The best model has the highest score. However, the score statistic is not a good measure to pick the best model among models with different number of predictors. Since there is high multicollinearity between x1 and x2, x4. We should choose between the first two models. The table on the right shows the first model with one predictor x1 and the second model with two predictors x2 and x4. The measures include R-squared, adjusted R-squared, Mallows CP, AIC, and BIC. All measures show that first model has a better fit than the second model. Also, a simple model is better. Thus, we should use the first model with predictor x1 as the overall best model. Again, we should not pick the best model among models with different number of predictors based on the score statistic. The best subset selection is computationally expensive when we need to consider many predictors. The number of all possible models is 2 to the power of p. When the number of predictors p is too large, the method will not be practical. Another popular selection procedure is stepwise regression. It alternates forward selection and backward elimination. Forward selection starts with nothing in the model and adds the most significant variable. Backward elimination starts with all the predictors and removes the least significant one. At each step of the stepwise regression, one variable may be added or removed. We may use different criteria in the variable selection. The most common one is p-value, but we may also use other measures such as R-squared, Mallows CP, AIC, BIC, etc. Different criteria may give different results. In the psychology example, we may use a p-value of 0.05 as the criteria and have a model that only includes x1. We may use other criteria such as a p-value of 0.1 or adjusted R-squared. Then we have another model that includes x1, x2, and x4. Of course, we know the second model has the multicollinearity issue. Here we ignore this issue and compare the model performance in the table below. The results show that the second model has a better performance. But we may still prefer the first model. Even the second model doesn't have collinearity issue for the following reasons. First, the simply is better. x2 and x4 may not be significant enough to be included in the model. Second, when we include more variables in the model, it is more likely to have overfitting. Third, the first model is easier to interpret. There are many factors we should consider for the best model if there is one. Our advice on the model selection is do not try to avoid the automated variable selection procedures, such as the stepwise regression. Even they are not perfect and may yield different results if different criteria are used. Do not ignore the multicollinearity during the model selection. Use cross-validation or test data to evaluate the model to prevent overfitting. Thus, it is also recommended to have the validation data that is totally independent data, especially for the model validation. In summary, we learned some important model selection ideas. When the model is not good enough, we may have an underfitted model. And similarly, when we mistakenly attribute part of the noise in the model may be overfitting. In practice, we usually randomly split all data into two sets, the training set and the test set. We develop the model based on the training data and only check the model performance based on the test data. Also, we may use k-fold cross-validation. We may have many different models for different training data. The mean squared error of the model is the sum of the squared model bias, the model variance, and the variance of the irreducible error. When we use a simple model with a few degrees of freedom, we may have high bias and low variance. When we use a complex model with many degrees of freedom, we may have low bias and high variance. The model that gives us the minimum test error is the appropriate model. When we add the interaction term in the regression model, the terms could be highly correlated and may inflate the standard errors, while the multicollinearity doesn't affect the coefficient estimation and the coefficient of determination. We need to select the predictors included in the model due to the possible overfitting. There are several guidelines that we should follow in the model selection. First, the simplest is best. Second, we should keep the lower order terms if we include the higher order terms in the model. Third, add or remove variables one at a time, preferably using the automated variable selection procedures. Last, consider the collinearity during the model selection. The best subset selection compares all possible models and finds the best model for the specified number of predictors, but it is computationally expensive and not practical if there are many predictors. Stepwise regression alternates forward selection and backward elimination. It may yield different results if different criteria are used. Do not ignore the multicollinearity during the model selection. Use cross-validation or test data to evaluate the model to prevent overfitting.